Welcome to Basic Mathematics Analysis class. Today we will discuss some theorems on limit of sequences. That is mainly, suppose you know some limits of a sequence. Okay, so suppose today what we are going to do is, suppose you know some limit of the sequence xn converges to x. Then what about modulus of xn? Sequence can be formed now from xn. Then in the same way, square root of xn. One sequence is like this, and the sequence is square root of positive square root of xn. Then what about these two sequences? Will it be converges, or will it converges to, as we are guessing, will it converges to mod x, and will it converges to root of x? And first of all, we will examine these two. So the first case, we are having a theorem 3.2.15 theorem. Let the sequence, let the sequence x equal to xn converges to x, converges to x, then the sequence, then the sequence modulus of xn of absolute values of abs sorry of absolute values converges to modulus of x. That is, if limit of xn is equal to x, then limit of modulus of xn is equal to mod x. So this is the thing we want to prove. So this can easily prove by using the inequality, right? So from triangle inequality, we get modulus of mod xn minus mod x is less than or equal to modulus of xn minus x. Will it be true? Take two values and check whether it is satisfied or not. Okay. Take some values and check whether it is existing or not. So we take 3 comma minus 4, right? So 3 comma minus 4 means you consider mod 3 and mod 4, right? Mod 3 is 3, mod of minus 4 is 4. Now you find what is modulus of 3 minus modulus of minus 4. So it will become 3 minus 4, that is minus 1. Now you find what is uh, modulus of 3 minus minus 4, right? So it will reduce as 3 plus 4, that is 7. So what you are having is modulus of mod 3 minus mod minus 4, right, is less than or equal to may come. In this case, is strictly less than modulus of 3 minus minus 4. So this can easily we can check this. So we have got this inequality. Okay. Next we are having xn is converges to x. It's given, right? Given sequence xn converges to x. So the sequence is converging to x. Then for given epsilon greater than 0, there exists some k belongs to set of natural numbers such that modulus of xn minus x is less than epsilon for every n greater than this k, right? Now call this as equation 2. Now you can compare those two, right? Now from 1 and 2, from 1 and 2 we get 1 and 2 we get modulus of mod xn minus mod x, this value which is less than epsilon, right? Which is less than epsilon for every n greater than k. And this implies the sequence mod xn converges to mod x, right? So we have proved that whenever xn converges to x, then modulus of xn converges to mod x. And next we have to prove that when xn is a sequence of real numbers that converges to x, and one more condition is that every term of the sequence is greater than 0, then the square root of the sequence, right? Root xn or positive square root converges and that limit is equal to root x. So next one, 3.1.16 theorem. 16 theorem. Let x equal to xn be a sequence of real numbers that converges to x, and suppose that xn greater than or equal to 0. This is very important. Xn greater than or equal to 0. Then this sequence square root of xn of positive square roots converges and limit of square root of xn will converges to, no need of saying that converges, we are written as limit, so it should be equal to square root of x. So what are the conditions? Xn is a sequence of real numbers of real non-negative numbers, I can say like that, non-negative numbers, then the sequence positive square root of xn converges and limit of that sequence is equal to root x. So proof. First note that first note that given xn greater than or equal to 0 for every n, then limit of xn greater than or equal to 0. So limit of xn is greater than or equal to 0. This follows from if every terms of the sequence are greater than 0, then limit of that also greater than 0 by theorem 3.2.4, right? So this implies that our x value is greater than or equal to 0, right? So first we will note that. For what purpose we are saying that x is greater than or equal to 0? In order to define this positive square root of x. So thus square root of x is well defined, or we can say that it's meaningful. It is meaningful. So first we are saying that the square root of x, we want to show that square root of xn will converges to x. That means positive square root. All the terms are non-negative. So we should take this x also non-negative. Then only we can define the positive square root. Now we will discuss this within two cases. We now consider we now consider the two cases. Two cases such that x equal to 0 and x greater than 0. So anyway x is greater than or equal to 0, and we will split this into two cases. So case 1, if x equal to 0, what will happen? Let epsilon greater than 0 be given since given that xn converges to x, that is x is 0, so xn converges to 0, there exists a natural number k such that if this n is greater than or equal to k, then we already know, you can say that modulus of xn minus 0 is less than epsilon, right? Xn minus 0 is less than epsilon. Also, we know that 0 less than or equal to xn. That means it's positive. And xn minus 0, modulus of xn minus 0 is nothing but xn itself now. So, what you're having is xn is less than epsilon, right? Therefore, what you're having is xn is less than epsilon, I am writing. right? So call this as your equation 1. Okay, equation. Also we know that also we know that for a comma b greater than or equal to 0, a less than b implies and implied by square root of a is less than square root of b. This too we have studied, right, by previous theorem. Therefore, what you're getting, 0 less than or equal to xn less than or equal to epsilon. Here we are having, right, which implies 0 less than or equal to square root of xn, which is less than square root of epsilon will come. But we want to get it is less than epsilon means what we have to do? We know that epsilon is we have taken. So you can go for epsilon square, right? No need of doing this epsilon square here, but in order to get here epsilon, I am doing this epsilon square, right? So this is less than, I will get it as epsilon for n greater than or equal to this k value. Now what will we get? Therefore, modulus of square root of xn minus 0 is less than epsilon, right? Since I have taken square root of xn means positive square root. So positive square root minus this is less than epsilon. Now since epsilon is arbitrary, we get square root of xn converges to square root of x. That is, what is square root of x? 0, right? So we will get this will, we have assumed that x equal to 0. That was our case 1. Do you remembering? X equal to 0. So in that case, we are getting this as 0. You remember here, I have started with epsilon. Now, in order to get here only, I have put epsilon square, right? Now, case 2. Case 2. What I want to assume? If x greater than 0, then root of x should be greater than 0, right? Also, we are having square root of xn minus square root of x. Modulus of this, we want to show that that is less than epsilon for some n greater than some constant value, right? Now, this can be written as this equal to square root of xn minus square root of x into square root of xn plus square root of x. We say that conjugate multiplication, right? Divided by square root of xn plus square root of x, right? Square root of xn minus square root of x into square root of xn plus square root of x by square root of xn plus square root of x. Now this will reduce as a minus b into a plus b form. So a square minus b square. That is root of xn square minus root of x square. That is xn minus x divided by square root of xn plus square root of x. Now this quantity is less than or equal to xn minus x by square root of x. Can I do like this? which is less than square root of x. What is the reason? Since we have assumed that square root of xn is a positive quantity, right? So inside the bracket we can note it down. Since xn greater than or equal to 0, therefore square root of xn is also greater than or equal to 0, and square root of x is also greater than 0, right? Then square root of xn plus square root of x should be greater than square root of x, right? Therefore 1 by square root of xn plus square root of x should be less than 1 by square root of x, right? So we have used that one here. So what should do next? Now we should consider modulus of this value. Therefore, modulus of square root of xn minus square root of x is less than or equal to, we will get 1 by square root of x into modulus of x minus x. So call this as your equation A, right? Now, since xn converges to x, given that xn converges to x, we get, what we will get? Square root of xn minus, sorry, modulus of square root of xn minus square root of x is less than 1 by square root of x into epsilon for every n greater than or equal to k dash, right? So this implies, since epsilon is arbitrary, see here also you can have this less than epsilon by taking, since xn converges to x, we get, what we get? For epsilon greater than 0, there exists some k belongs to, or k dash belongs to n such that your condition should be modulus of xn minus x is less than, is the epsilon by, or I can go for root x into epsilon, right? Root x into epsilon. Since root x is greater than 0, this is should be greater than 0, so you can replace that. So you will get here exactly epsilon, right? So if you need means we can have this like this, but it's no need here because since epsilon is arbitrary, now since epsilon is arbitrary, we can conclude that modulus of, sorry, square root of xn, that sequence converges to square root of x. So we have proved that one. Next we have got one more theorem, 3.2.17 theorem. Let xn be a sequence of positive real numbers such that such that L equal to limit of xn plus 1 by xn exist. Now, if this L value is less than 1, then the sequence xn converges and limit of this xn is equal to 0. So whenever you are having, what's the meaning of this? See, you got a sequence like this. Suppose you have got a sequence. See, suppose you have got a sequence like this. That is, sequence is x1, x2, x3, x4, xy, etc. Some x100, etc. This is your sequence, right? Now you calculate this one, x2 by x1. Like that ratios you can calculate now. So you take a general term. So xn should be there now. Next term should be xn plus 1. So you take that time. That is xn plus 1 by xn. This is a new sequence. Now this new sequence we will get for n equal to 1 onwards only it is defined. So we will get x2 by x1. First time x2 by x1. Second time x3 by x2. Next time x4 by x3. Next time x5 by x4. Like that the term. Now suppose this sequence converges to L and limit of that is less than 1. Then what we are going to find is that this limit of this sequence then will converges to, this sequence will converges to, if this is the case means we will get your sequence xn, that is this one, will converges to 0. So we want to prove this. I think you're clear with this theorem. So I'm moving to proof. Proof. Since your xn is greater than 0, sequence of positive real numbers given by theorem 3.2.4. What was that? If each term of a sequence are greater than 0, then limit of that sequence is also greater than 0, right? Then we get this L is greater than or equal to 0. Then again this ratio, right? Let, we'll change the ink. Let R be a number, be a number such that L less than R less than 1, and let epsilon is equal to R minus L. Then epsilon is greater than 0. Then there exists a number there exists a number k belongs to n set of natural numbers. K belongs to n such that if your n value is greater than or equal to k, then modulus of x n plus 1 by xn minus L is less than epsilon, right? Just we have used the convergence of definition of convergence of the sequence xn plus 1 by xn. That is minus epsilon less than xn plus 1 by xn, which is minus L, right, is less than epsilon for all n greater than or equal to k. Or that is, what you're getting is minus epsilon plus L less than xn plus 1 by xn, which is less than L plus epsilon for all n greater than or equal to k. Now we will take only this part, right? That is xn plus 1 by xn is less than L plus, what's your epsilon? You have taken epsilon as this r minus L. That's why I have taken epsilon as r minus L. So I'm taking this as r minus L. So what I'm getting is equal to L. So I'm getting x n plus 1 by xn is less than r, or that is I'll get x n plus 1 is less than r into xn, right? Less than r into xn. Now you can note here one more thing. What we are going to note here is, now we have got x n plus 1 is less than r into xn. Now suppose I want to have xn, right? Suppose I am proceeding like this. Now I will find what is xn by uh, xn minus 1, right? So xn by xn minus 1, again I will get which is less than r, right? So from this I will get my xn is less than r into xn minus 1, right? So xn is less than r into xn minus 1. So from this I will get xn plus 1, which is less than r into xn, which is further less than, xn is less than this, so r into xn minus 1, or that's equal to r square into xn minus 1. So similarly you will get, I have taken xn, right? So I should further xn minus 1 by xn minus 2, which is further less than r. So that implies your xn minus 1 is less than r into xn minus 2, right? So what you want to do? So again applying this to further, right? Okay, so from this we'll get like this. So again, sorry for that. See, again we should use this one. So xn plus 1 is less than, I'm getting as r square into xn minus 1, right? So what I will get from here, xn minus 1 is again less than r into xn minus 2. So if I am using this again, okay, suppose I am using this again, what I will get my see, from here I'm having r square into n minus 1. So I will get from here x n plus 1, which is less than r into n, which is less than r square into x n minus 1 up to here. Now next case, I'll get this is less than r into x n minus 2, and this value is less than r square into r into x n minus 1 less than this r into x n minus 2, right? So what I got now, x n plus 1 less than r into xn, which is less than r square into xn minus 1, which is less than r cube into xn minus 2, etc. Right? So I will get like this. Now I will copy it here. Therefore, if my n is greater than k, then only this condition holds. We get we get 0 less than xn plus 1, which is less than xn into r, which is less than xn minus 1 into r square, less than, etc., less than, I'm taking a common term, xk r raised to, what will become, x raised to n minus k plus 1, n minus k plus 1. So from this you are getting 0 less than 0 less than xn plus 1 less than xk r raised to n minus k plus 1, right? From this. Now if you are put c equal to xk by r raised to k. R raised to minus k is there, so it is r raised to k will come, right? We get, what do we get? 0 less than xn plus 1, which is less than c into r raised to n plus 1, n plus 1 for all n greater than or equal to k, right? Now where this r belongs to? In between 0 and 1, right? This r, see, you have taken r be a number such that r is in between l and 1, but l is greater than 0, so it is in between 0 and 1. So what we can conclude? Since 0 less than r less than 1, then limit of r raised to n plus 1 should be, or r raised to n should be 0, right? Limit of that should be equal to 0. Then we are having a theorem 3.1.10, then by theorem 3.1.10. What was that? 3.1.10 theorem. If anybody is remembering, it says some constant is given, then whose value is less than c value is greater than 0, then mod xn minus x less than or equal to c into an for all n greater than m, then limit of if an equal to 0, then limit of xn equal to x, right? So refer the theorem. Then by theorem we get, see this part, this sequence converges to 0. So this part also will converges to 0. We get your sequence xn converges to 0. Sequence xn converges to 0. And we can verify this using an example. It's an example. Consider the sequence. Consider the sequence xn given by xn equal to n by 2 raised to n. Sequence is n by 2 raised to n. Now we want to calculate the ratio, right? Xn plus 1 by xn. We have xn plus 1 by xn. If this is having a limiting value which is less than 1, then only we can apply this, right? And this equal to, what should be the n plus 1th term? So n plus 1 by 2 raised to n plus 1 into, I can put the reverse, right? Or the reciprocal. So xn should be 2 raised to n by n. So when you are multiplying, cancelling this 2, I will get a 1 by 2. So 1 by 2n into n plus 1 will come, right? Or I can have this as 1 by 2 into 1 plus 1 by n, right? Thus, limit of xn plus 1 by xn, right, is equal to, this limit you know, it is as 1, is equal to 1 by 2, right, which is less than 1. So we can use the previous condition, right? Now it follows from above theorem that the original sequence, okay, that limit of n by 2 raised to n is equal to 0, right? This we have proved. See, another way of looking at this sequence is like this. See, your okay. Another way is, you're having xn equal to n by 2 raised to n, right? So when n is increasing, 2 raised to n is increasing very largely, right? So we take like this, for n equal to 3, what will happen? Numerator is 3, but denominator is 2 raised to n, that is 2 raised to 3, 8, right? When n equal to 4, n 4, 2 raised to n will become into 2, right? 16. So when n equal to 5, 2 raised to n will become 16 into 2, 32, right? So whenever you are having this value, here rapid increase is occurring, right? So in the denominator, a rapid increase is occurring than the numerator. So you will have here bigger quantities, bigger and bigger quantities is coming. So when you're taking the limit, means you will get some small quantity by a big quantity. So we will say that this is approximately equal to 0, right? So this is an informal way of just a comparison of these two. Since this denominator is not equal to 0 for any n, we can just compare and do like this. So evidently this sequence limit should be equal to 0, right? But here we have professionally proved it, right? I can say like that. We have professionally proved this, and this is an amateur work. Okay, so I'm winding up today's session here. Thank you for your patient listening. Thank you.